Here's the beginning of topic 4, talking about oscillations and simple harmonic motion. So we'll first start off with your definition of oscillations here. An effect expressible as a quantity that repeatedly and regularly fluctuates. So it's repeated above and below some mean value, and that mean value is like your average, right? It's like the average of above and below would be like your equilibrium position. So this is like at rest. Your equilibrium position is at rest. So on a pendulum, it's just hanging there, okay? So then you're going to pull it back to some different displacement, i.e. amplitude. You're going to leave go. It's going to oscillate back through and back to the beginning. So like from position A to equilibrium to B to equilibrium back to A. Okay, so that's what we're thinking about there. So just think about, well, like the Newton cradle that's on my desk. So you grab one of those balls and the energy is transferred from one to the next, and then the end one is so far out. And then the end one hits the middle ones, and then the other end one is now so far out. So just think about that motion here. You'll also see it in mass spring systems where you're going to see a mass vibrating up and down and up and down and up and down and up and down. We'll also be showing these examples in class. So your two that we're going to concentrate on are a simple pendulum. And on a simple pendulum, I'm just going to cut to the chase real quick. Your length and your acceleration due to gravity are going to be two very defining variables inevitably. And then the second one we're going to concentrate on are mass spring systems. And in a mass spring system, you're going to look at what's called the spring constant, and you're going to look at your force as well that's dealing with this, obviously coming from the mass. All right, so continuing with this then. Let's look at these objects and see if they do demonstrate oscillations. Once again, this is like a repeated path going back and forth, back and forth. So you pluck the strings on a guitar, it vibrates. Is that showing oscillations? Strings on the piano keys after being struck, is that showing oscillations? So think about these examples as I'm saying them, guys. Waves of water after a rock has fallen into the water, so you look at those different ripples. Spiders detecting prey due to the vibrations felt on their webs. Being able to listen to your favorite radio station, obviously through the speakers. Atoms vibrating within a molecule. So all these are examples of oscillations. Next, we have some vocab terms that you need to be familiar with, and the first is amplitude. Please notice how your amplitude is going to be measured in either X or X sub O. I'm really going to try hard to stick not American on this one and go international. So you're going to see a lot of those variables that are in your data booklet on this. So for instance, the amplitude X, or like initial amplitude X sub O. Definition here is maximum displacement from the equilibrium position. So how far did you pull this string back? Okay, so that would be like looking at your amplitude, how far this string was pulled back. Furthermore, well, and it's going to be measured in meters. Metric system there, you know, international units, literally from the French, it's going to be spelled with an R-E instead of an E-R. All right, so furthermore on that, when we look at this system, we're going to look at how you're swinging this way, and then you're coming back and swinging that way. Okay, so it's just a continuous motion of back and forth. That's what your pendulum is doing. Now, if you were to graph what this pendulum is doing, then you would literally see I'm swinging this way to my equilibrium position and then to my furthest point, to my equilibrium, to my furthest point, to my equilibrium, to my furthest point, back to equilibrium, right? So you're going to be able to see how this thing is moving, i.e. oscillating, as it's traveling from one position to the next. In other words, displacement of it. Does that make sense? So we call these sinusoidal waves, like here would be your x-axis, and you're looking at your negative amplitude and your positive amplitude, because once again, we're talking about a displacement. So your amplitude is probably going to be a positive or a negative value throughout this system. Now I bring this up because eventually we will be graphing whatever you are seeing. So you're going to take your data, plot it, turn them into some sinusoidal graphs, sine waves versus cosine waves. More so we're going to stick with sine waves, but we're going to use cosine a lot. Little side note, please make sure you're in degrees. Okay, next one that we have is a cycle. Cycle is one complete oscillation from the beginning to the end, and cannot stress this enough, and back to the beginning. So if you're just saying like your pendulum's here at rest and I swung this way and then I swung that way, and that's one complete cycle, that's not true. It's from here back to where you started from. 1, 2, okay? So that's what you really want to look at there when you talk about an oscillation and then completing a complete cycle, one complete cycle. In circular motion, it's going once around the circle. So that's why I threw this example in here. And once again, you can look at your graphing here. So max amplitude, back to equilibrium, to max negative amplitude, back to equilibrium, back to max, etc., etc. I'm sure a lot of us have seen this in math class before. You haven't been introduced to this t yet. This t is going to be period. It'll be the next variable vocab term that we'll be discussing. So with that in mind, time period, which is a capital T, is the time it takes for one complete cycle to occur. So this is going to be measured in seconds. Okay, it'll be measured in seconds. So once again, here is like our equilibrium position right here. Okay, so this is your equilibrium. So you're looking at your positive amplitude, you're looking at your negative amplitude. I started right here, okay? So the pendulum swung past equilibrium to its maximum displacement on the other side, back past equilibrium to its maximum displacement that I started from. So that would be one complete period right there. They're taking from right here to right here is also one period. Take a second and assess that, guys. Let me do that one in green, just so we have a different color to relay this to. So they're saying, okay, so now instead of pulling it to the right and letting go, I'm going to start pulling it from the left side, negative, and letting it go. So it went from the left past equilibrium to the right, back past equilibrium to the left again. So would it be true that this equals one complete period, one complete cycle? Measured in seconds, just to be a little bit more specific. So yeah, you would be able to say that this is one period that you are dealing with in this system, measured in time, which is a t, which is also going to be in seconds. Amplitude would be in meters. Furthermore, we want to look at frequency now. Frequency is a lowercase f, and for your frequency, you're going to look at it as the number of cycles, so the number of periods that the pendulum makes per unit of time. Per time. So time's going to be in our denominator here. Remember, if you see per, this means like divided by is pretty much what you can interject there for that. So you're looking at 1 over the time period. In other words, 1 over capital T. Well, that would be 1 over S, but we really know that as s to the negative first is what we would label that as. But an s to the negative first is also known as a hertz, in which hertz is abbreviated as a capital H and a lowercase z. So these two units are the ones that I want you to be familiar with when we talk about frequency. Your frequency can be measured in per seconds. Makes sense, right? 1 over an s is a per second. We just put all of our units in the numerator, so s to the negative first. S to the negative first is also known as a hertz. Please take a second and assess this graph. Doesn't this make like total sense? And can't you see here how this is also an applicable equation? That your period is 1 over f because f equals 1 over t. All you did was just rearrange it. Multiply both sides by t. Therefore, TF are going to be indirectly related to each other. Okay, indirectly related to each other there. Moving right along now, we have angular frequency. And angular frequency is like the Greek letter for the lowercase letter w. It's not a lowercase just w, it's like Greek. It's kind of like rounded w like that. Okay. Anyways, this is used when describing circular motion. And with that, what we're going to look at is 1 revolution. So, you know, you revolve around the circle, so like 1 revolution versus a rotation per second. 1 revolution per second. And that's going to be 2 pi rads s to the negative first, right? Your radians is what we're talking about here because we're talking about circular motion. Okay, so you're going to calculate this by multiplying your frequency by 2 pi. So in other words, your angular frequency is going to equal 2 pi f. 2 pi f. Okay, so let's look at it when it's used to describe an oscillation. This is meaning that the 2 is equivalent to 1 complete, I'm sure some of you guessed it, cycle. Oops, 1 complete cycle. 1 complete cycle. So what would the variable be that you want to use here to denote 1 complete cycle? That would be a capital T, right? Okay, so with that in mind, you got 1 over T again, right? Is equivalent to, 2 is equivalent to the 1 complete cycle, so that would be your s to the negative first, or what was the other units? Like, what's 1 over s mean, guys? 1 over s simply means hertz. So your angular frequency and just like straightforward frequency are both going to be measured using the same units. So here's our sample problem here. Pendulum completes 10 swings in 8 seconds. Calculate the angular frequency. Okay, so the number of swings that we have is 10, and the time in which it completed that was 8 seconds. And we want our angular frequency, which is going to be measured in, we'll just stick with hertz. Is that true though? You'll find out in a second, no. So I'll just put a couple of question marks beside that. Okay, so period is going to be your swings per time. Therefore, your period equals 10 over 8, which is 0.8 seconds. Okay, 0.8 seconds. It's not a final answer, so we're not going to box it or anything there. But then we know that frequency is really 1 over t, so that's really going to give us 1 over 0.8, which our calculated answer comes out to be 1.25. We're not at the end yet, so let's not, do sig figs. Let's try to hold through on this. So our angular momentum is 2 pi f, which would give us 2 pi times 1.25. Your calculated answer there is 7.85, which means that your angular momentum is technically 8. Let me erase that and write that down. 8. And now here's the trick. It's going to be rads per second. Okay, because we're talking about circular on this one, okay? So rads per second. So frequency and angular momentum with the acceleration is going to be A equals negative angular momentum squared times your displacement. So this is like a quantity. Remember that the negative is showing a vector quantity, okay? So the example here, just due to time constraints, guys, your example here is going to say that your period is 2.00 seconds and that your displacement is 1.00 meters. So your original equation is simply this, which would be negative 2 pi over t squared times times x. Let's just stick that. So that would be negative 2 pi over 2.00 squared times 1.00. Quick math here. 2 divided by 2 is 1. So all you're doing is 3.14 squared, but it's negative 3.14 squared. So that's going to give you 859. So your acceleration equals negative 9.86 meters per second squared. Okay, in the next video, we'll move on to our next concept about phase differences.